Hi there, this is JNEL with Unit 1.1, Lesson 4 on inclined planes. That is the fourth simple machine that there is in Principles of Engineering that's taught. So, let's get into that. So, the actual definition of an inclined plane is a flat surface set at an angle or incline with no moving parts, and it is able to lift objects by pushing or pulling the load. That's the PLTW definition. And I think that, like, out of all of them, it seems like that inclined planes and wedges seem to be some of the simplest ones. I think that sometimes wheel and axle and pulley and screw can be a little bit difficult, and lever isn't that hard to me either, but that's just me. So here is a picture of an inclined plane. Now, when you'll see a problem, it will just be a triangle, but I try to make it kind of look 3D. But let's just pretend that this is like a certain length, and then up here is a truck. So that this could be the road, and then they're trying to unload something from this point to this point. And they're not just going to, oh, hey, throw that off. No, that's bad. You wouldn't want to do that. So you can just put an inclined plane there, which maybe is just a kind of ramp. And really the triangle that they're using in the problems would be this. What I have just now done in blue, that's what the triangle would be. So, first, we'll talk about how to solve for the IMA. So we know IMA is dE over dr, but for inclined planes, you don't really need to do that because the dE is the L that's on here, and the dr is the H, so it's just L over H. And so, if you'll notice in the next video, lesson 5, that's the same formula for the IMA as a wedge, but the L and H are at different sides of the triangle for a wedge. So don't get confused about that. So that is how you would solve for IMA. So let's pretend that this is 3. This length is 3, this red. And this is 4. And what is the IMA by that? Well, this is actually a multi-step problem because we know to solve for the IMA you have to do L over H, but you're only given what H is, which it's 4. But what is L? Well, if you watched any of the geometry videos, this is kind of back into that. Oh, why did it do that? You know, to find a missing side on the triangle, you can use, hang on a second. You can use, the Pythagorean theorem. And if you never took geometry, then you are like, hey, what in the world is that? Well, that is, a formula that is a squared plus b squared is c squared. And that might just seem like gibberish to you if you've never heard of it, but certain sides can be labeled A, B, and C of a triangle. So let's label this side A and this side B. Oh, and sorry, something I left out. It has to be a right triangle, which would have that marking. So A and B can be used or named or labeled interchangeably, because they are both the sides that make up the right angle, but C has to be the side that's directly across from the right angle, which would be this. So that's C. So since we we can solve for that way. So A is 3. So 3 squared plus B. B and H are pretty much the same thing, which is 4. So 4 squared, which equals C squared. We don't know that, so we're going to solve for that. And so now we can solve. 3 squared is 9. 4 squared is 16, which is C, and then equals C squared. 9 plus 16 equals 25, which still equals C squared. Now what you have to do is take the square root of both of those, because that's the inverse operation of squared. So 25 squared, or sorry, square root of 25 is 5. And some people probably already knew that that's what L was going to be, because, or C, because there's a 3, 4, 5 triangle rule. So if A and B are 3 and 4, you already know that C is 5. But and I knew that. I just was solving it in case you didn't. So let's actually just clear that all off now. So let's redraw this triangle. And if you notice it like does dots like that, I think it's because this device I'm using was one time shattered, so maybe the people that put the glass on didn't do such a good job or something. I don't know. So this, once again, that's H, that is L. We already knew that H was 4, and we just found out that L was 5. So now we can do the IMA. So remember, IMA is L divided by H, which we know L is 5 and H is 4. So when you solve that, you find out that the IMA is 1.25. And, well, technically there would be units. Let's just pretend that was feet. But they would cancel out anyways right here. So the IMA is 1.25. But the AMA is a little bit different. So there wasn't anything that even showed any forces. We only knew the lengths, DE and DR. But the only way that there could be forces is if there was something that was going on the inclined plane. So let's pretend they were driving a cart down the inclined plane. So there's a truck up here that's like, okay, let's unload some materials to this Home Depot or whatever. So sorry. Let's say in the cart there is 127 pounds worth of materials. And since it's going down it, there is a force of 20 pounds that is used to push that cart. What is the AMA? So the AMA is FR divided by FE. This would be what I'm about to do in red. That is the effort force, because they're using that effort to push it. This would be in blue the resistance force, because that's what's in there that's keeping it stable. So let's delete that again. So let's remember IMA was 1.25. And then the AMA, since that's resistance force, which was 127 pounds divided by 20 pounds, the pounds cancel out. So that is 6.35 exactly, not approximately. So that's the AMA and IMA. So we want to know the percent efficiency. That is AMA divided by IMA times 100. So that would be 6.35 divided by 1.25 times 100. 6.35. That is 5.08 times 100 would equal 508%. So you're like, what in the world? Why is it so high? Well, if you remember, for one thing, the numerator right here is very high compared to the denominator. And also, if you notice in the problem, they were pushing the cart down the ramp. You don't need that much effort to push it down the ramp. So that changed the equations, because it was efficient for the cart going down, obviously, because it's easy to push something down instead of up. So if they're pushing it up, then they might have needed more force, which would have caused the AMA to be lower, which would have caused the percent efficiency to be lower also. But for pushing a cart downhill, that would make a very good ramp. Or sorry, incline plane. So that would be it. Thanks for watching, and please see the other videos for more help. Thank you.